All right, so let's look at a couple example energy graphs. All right, Mrs. Higgins showed those to you yesterday. Let's go ahead and say you have a graph that looks like this. What's that going to tell us about that? What that reaction looks like? Well, we know it's endothermic because our delta H, right, our change in reaction energy is positive, so that's endothermic. So if that was happening in your hands, it's absorbing energy from your hands and it would feel cold. I don't love to obsess about the feels hot, feels cold thing. That works great in junior high. It works great for a lot of things we do, but we can kind of confuse things a little bit. Because water boiling is also endothermic, but that feels, you would certainly say it's hot. But to the stove, the water boiling would be cold, right? Because the boiling water is absorbing energy from the stove. But this would be endothermic. We've got a pretty high activation energy here, right? That's a larger activation energy, so that would make it a reaction that would maybe be a little slower. If I compared it to like that reaction, right? This reaction would be a little faster. We've added a catalyst, or I could add an inhibitor, right? That would slow the reaction down, something like that. But all those would be the same endothermic kind of thing, just different pathways on that same endothermic thing. Right? If I flip it then and go like this, that would be exothermic. That would have a fairly low activation energy, right? Our activation energy is just right here. That's not a very high activation energy, and it's exothermic. So imagine if we did one like that. What would that mean, right? Would this reaction be very hard to make happen? I would say no, right? It has an activation energy, but it's a very low activation energy. And is it endothermic or exothermic? Right? It's exothermic, right? You have a large release of energy. So it's a reaction that happens very easily and then releases a lot of energy. So this would be a lot like the decomposition of NI3. NI3 is what we call a contact explosive. Contact explosive. That means you just have to kind of touch it and it'll make it explode. So kind of a fun little chemical that we like to make every year. Unfortunately, you don't get to be here to see it, but it's kind of fun to look at, right? So I have a couple of videos where I made it for AP Chem because actually we were doing a different thing with the same idea. So this is has a very low activation energy, releases a lot of energy, so it's a contact explosive. Let's expand our chemistry a little bit, think back to other stuff. Why? So if I did my Lewis structure for NI3, you end up with this Lewis structure, right? Iodine has 7 valence electrons each. It likes to bond 1 time, right? Nitrogen has 5 valence electrons. It likes to bond 3 times. You end up with however many valence electrons you end up with. I don't remember. But you've got a shape like this. So if we think back to our shapes, I have 1, 2, 3, 4 regions of electrons. 4 regions of electrons, 3 of those being bond, would be a trigonal pyramidal shape, right? So you end up with a shape like this. Well, there's lots of things that are trigonal pyramidal that are not contact explosives, but nitrogen triiodide is, right? So then we think, well, how come? Why is it that this is so unstable, right? A contact explosive would be really unstable. It's got 8 valence electrons. Students tend to really, it must not have a stable 8 set of electrons. Well, it's not a lot of times something like that. This, on paper, looks like it would be fine. Now we start thinking periodic chart style, right? Where's nitrogen on your periodic chart? It's in the 2nd energy level. So is it very big? No, right? It's just a little 1s2. Look at how many chapters we're hitting all with this one demo. 1s2, 2s2, 2p3. So its electrons are in the 2nd energy level. Iodine is in the, 5th energy level? Because you've got fluorine, chlorine, bromine, iodine. 5th energy level. So this would end in 5p5. So it's in the 5th energy level. What's true size-wise in the 2nd energy level versus the 5th energy level? The 5th energy level is a lot bigger, right? So iodine is a really big molecule. So if we start thinking about this, I have 1 small atom in the middle and 3 large atoms on the outside. So if we start picturing this in our head, right? To be good science students, we do need to have some creative thought process. You need to be able to picture what's going on in your head. So if I take a little tiny nitrogen, here's my nitrogen. I tried to put 3 pieces of tape kind of towards the bottom of this guy. And then there's 1 iodine bonded to it. And here's another iodine bonded to it. And here's, I didn't have all same color things, right? And here's another item. You can start to see there's not much space there. So that's what you get, what's called steric hindrance, right? And the term isn't all that critical, but it's that there's physical strain. These guys are, remember, bond angles, when we looked at those, it's 109 degrees. So that, yeah, it's got a 109-degree bond angle, and you've got this lone pair here and stuff, but it's really, it's tight, right? It doesn't have as much space as it would like. It would like to be able to spread out a lot more. Iodine is big, and so when we're trying to shove these guys really close together, it doesn't fit very well. So it's a lot of steric hindrance. So with just a little bit of help, we can break these bonds. These are long, weak bonds, and form new bonds that are much stronger, right? So when we break weak bonds and form strong bonds, we release a lot of energy. So that is our nitrogen triiodide, our contact explosive. I have those drying over on the other side of the room, and tomorrow we'll, because you make it wet. It's an, sorry, let me back up. I make it, and it's a very endothermic reaction. It gets really, really cold, and it's stable as long as it's wet, because the water kind of helps float all those bonds. But once the water dries in, it's a contact explosive. So I leave it set on filter papers overnight, and then I'll come in tomorrow, and we'll tap them, and hopefully they'll go off nicely. I've got a few videos from AP Chem, but I had trouble getting very big ones to go. It was, I can only get the smaller ones to go. So I'll put all those videos in there because it's kind of fun to watch it. But anyway, we'll pick this up in about 1 second for you, but like tomorrow for me, right? You know how that works. So I set up nitrogen triiodide. I came back in this morning, and my room was weird. Like, there were paper towels like that I'd used to clean stuff up that looked like they maybe exploded in the trash can. I think maybe somebody rifled in the trash and pulled them out. I'm not really sure. There was a rubber glove that had like iodine stains on it. Iodine tends to stain things orange when you touch it. And so the nitrogen triiodide, when that breaks down into solution, it can turn a lot of things orange. The gas itself is actually purple, but iodine things are big. Depending on who they're bonded to, they form different compounds and colors. The filter papers that I left the stuff on were like completely exploded and spread out over them. So it seemed like somebody had been in my room and messed with this stuff. I hope somebody didn't get hurt in my room. I didn't get any emails from any, but I was under the impression there were no custodians coming up. So I don't know who was doing what, but I will probably try again maybe over the weekend. So we'll see if I can get a good one. I've got a couple like ones from the past, so I'll link those right here. But if I get a better one, we'll tick that one on there too. But anyway, here we'll go ahead and go to some from the past. They're not like as good as in person. These are so much more fun. So that's what it looks like. It's that brown stuff there in the middle of the filter paper. We've got 3 of them, so hopefully at least we can get 1 or 2 of them to pop pretty nicely for us. So I'm going to set you there. Got a little meter stick with a feather on it, and we'll give it a try.